I was asked to re-record Peter and my talk at the MOC Alliance workshop because of some problems with the recording. So it was better in real life. So this project is the work of a really large community that have contributed to all of this. I've tried to include names and original affiliations, but please forgive me if I missed you. The cloud has fundamentally transformed research and innovation. For domain researchers that want to use the cloud, it's become the new library where data is discovered and the new laboratory where a lot of science is done. For system researchers like Peter and myself, it's enabled rapid transition from research ideas to experimental services to production operations, informed by the real usage of a cloud. Unfortunately, the public cloud today is a problem for domain researchers that the cloud lacks the facilitators that are so important for high performance computing. It can be unpredictably expensive and it kind of locks you into a particular public cloud. For system researchers, most of the academic research and open source community, even a lot of industry is actually locked out of innovation in today's public cloud. So back in 2013, we had this crazy vision to create our own cloud, the mass open cloud. The idea was we'd have real production services that domain researchers could use. We would inform systems research by the problems we were seeing in a real cloud. And that would in turn result in innovation in open source that could actually be transferred back into our own cloud. In other words, we wanted to create that rapid innovation loop that's going for systems research and hyperscalers, but extend it to broader academic community and the open source community. It actually worked. There's a whole series of projects now staying up production cloud services, enabling research, enabling that research to impact open source and transitioning that innovation back into the production cloud services. Major projects are run by research IT and rather than just our own soft money efforts. And as a result, we've actually formed a formal structure that actually gives us the legal agreements and the governance for the larger effort. And critical from my perspective, we're going to be rolling out a billing model that'll enable this entire thing to grow in a self-sustaining fashion. The scale that's made possible by the MJHPCC, the enormous demand for cloud computing from academic researchers, and incredible innovation from the engaged system research, open source, and industry partner community. You're going to hear from a lot of others in the workshop about the projects that are doing the real work. But Peter and I want to focus in this presentation on how the Alliance has succeeded in having research informed by the problems of real cloud and how that's impacted open source and actually resulted in products and changes to products that in turn impacted our own production cloud. So I'm sorry, this is a bit of an eyesore, but red efforts, orange efforts are affiliate projects of the MOC Alliance, red are research efforts, and green are things that have actually impacted open source and make haste be transitioned into products. And each of these efforts has a talk or a poster or represented in a BOF in the workshop. So of course, started with the MJHPCC, a shared data center of massive scale, 65 megawatts, that creates a common environment where all this innovation can happen. The MJHPCC enabled us to kick off the mass open cloud, and the efforts and engagement in that resulted in Red Hat creating the collaboratory that funded a lot of the research that I'm going to be talking about. One of the first things we wanted to do was support systems researchers that needed physical hardware. Projects like Jonathan Apavu's operating system research on unikernels. We also wanted to find ways of partitioning our hardware for staging and production and ways to share hardware with other projects. So I still remember in the early day, we talked to some of the HPC clusters, in fact, Saul Yosef, and asked them, can we share hardware with you? And he sort of looked like, why? I run my hardware at 95% utilization. What value could I get out of sharing with you? And we said, well, we're an interactive cloud. We expect often to be running at 20, 30% utilization. What if we gave you 100 servers 9 days out of 10, we asked for 50 servers on the 10th day? He said, well, you guys are idiots, but yeah, I'd love to share hardware with you. So we ended up developing a research project, the hardware isolation layer, with the goal of developing a service that would allow computers to be moved between different clusters in the data center, not requiring any changes to the cluster software. That was successful, ended up getting used by us in production. But increasingly over time, we realized we wanted to do this rapidly. The effort of installing the software into the local disks really offered a lot of problems for that elasticity. And also security was a major concern. We had the CRISP project you're going to hear about that wanted to do analytics from Boston Children's Hospital into the cloud environment. So we started thinking a lot about security, and eventually we ended up developing BMI, which was a disaggregated storage service, Keyline, which is an attestation service, and secure firmware. And this is joint work with 2 Sigma, Red Hat, MIT Lincoln Labs, and the US Air Force. As a result of this work, Keyline is now green. It's actually as a broad open source community. It's actually deployed in production in IBM's cloud. It also resulted in a project, Elastic Secure Infrastructure, that recreated the capabilities of Hill and BMI using components out of OpenStack, Ironic and Neutron. This project is now production or nearing production. It's on trial in MGHPC, where all kinds of different clusters are starting to use it and experiment with it. Having a production quality implementation enabled other research, such as the marketplace-based DSI that is developing market mechanisms to incentivize clusters to trade resources, not only when they're idle, but when other clusters have major demand. It also enabled the Open Cloud Testbed, which is an elastic testbed with accelerators, an environment where anybody can allocate bare metal hardware. The Open Cloud Testbed differs from other testbeds in that instead of it being fixed infrastructure, it can grow and shrink depending on demand. And this is a major problem. If you look at the other testbeds, they're set up on a fixed infrastructure for a community that all has the same publication deadline. Being able to grow or shrink the testbed depending on need is kind of a huge differentiator. We also added bump in the wire FPGAs as a novel capability for system researchers, which resulted in environments such as CODES that you'll hear later on to enable sort of low-level experimentation with FPGAs. One of the things we learned running the MOC was how to run Ceph, large-scale distributed storage infrastructure. That resulted in turn of the Northeastern Storage Exchange, which is a large project. Today, it's about 50 petabytes of hard drive storage, a large Ceph pool, and 130 petabytes of tape that can be shared between all the different institutions. As researchers, we spent a lot of time looking at that object storage. And if you do this on high capacity drives located in one place in the data center, it results in real problems when you're trying to access it for data analytics, for example. So we ended up working with the Ceph community to modify the Rados Gateway, which is the S3 implementation of Ceph, to first incorporate with D3 and read caching, and then with D4N, a write-back tier. And that's actually the D3N is already upstreamed. It's in Ceph. You can use it if you have your own cloud, and D4N is in the process of being upstreamed. We also looked at frameworks like Spark and the job queue and extract that information so we know what data is going to be accessed, so we could actually do prefetching into the cache based on future accesses that we're expecting. So this has been very effective. The Open Storage Network was another project that we mentioned, which has these 1 petabyte data lakes around the country. You're going to be hearing about the kind of storage we're doing now on hybrid cloud storage that will enable data to follow you as you kind of move between our cloud and regions of AWS, for example. So volume storage is still a real problem. So if, today it used to make sense to run volume storage on Ceph distributed across a whole bunch of disks, but with the high speed of SSDs, it becomes really difficult to compete. And we needed to develop some mechanism that would allow us to continue to have disaggregated storage. So we ended up developing a capability called the Lux Structured Virtual Disk that uses the local SSD just as a write, log, and read cache, and writes these large batches out to object storage, and preserves consistency even when an SSD fails. This ends up giving it a massive performance advantage. So there's a Eurysys paper, but it's actually all going upstream right now into Ceph. So that had a very major impact. We ended up supporting many users, and indirectly thousands of users of services stood up by those users. But the MOC has always been a best effort system with really no guarantee, no facilities, and a lot of skill required from the users, and frankly, risk tolerance as well. So as a result of all this work going on, a couple of years ago, BU and Harvard made the decision it's time to stand up real production services. NERC has a shared effort where a team from Harvard and BU that decades of operating massive HPC clusters are operating it, and teams from the former MOC's operations team and Red Hat Research have been working to actually create the production services they can actually operate. Having the NERC ended up resulting in new projects, AI research like AI ops that could actually go and study that. But while this was going on, there was still a lot of innovation at that low-level operating system layer. So SUSE was a project that focused on the cold start problem serverless. BAOPS is a project you're going to be hearing about that ended up using machine learning to control certain hardware characteristics, resulting in an energy savings of over half for some interesting workloads. And more recently, a new project called UKL, Unikernel Linux, that's about to appear in Eurysys, but brought those capabilities of unikernels into Linux. You can actually take your application and compile it into the Linux kernel itself. To be honest, I never thought this project would be successful. It took many years of iteration with weekly meetings of teams of engineers from Red Hat working with students to find a mechanism to incorporate this into a clean way. And there's a patch that's currently under review on the Linux kernel mailing list. That capability of now having a unikernel that could be production has enabled projects like Secrecy, which is a multi-party computation environment that really wants low latency communication. So this is an MPC as a service offering with innovative approach for optimizing queries. And they actually envision query optimization that's configuring low-level OS optimization. So this couldn't have happened if UKL wasn't sort of integrated to a rich environment, but now other research can depend on that kind of research. Another low-level core OS project is Morphos that's found literally dozens of bugs inside QEMU and is now upstreamed and as a part of QEMU, and every commit goes through it, doing fuzz testing. As a result of Production Cloud, there's now dozens of interns, or there have been dozens and dozens of interns get engaged in the education on a yearly basis. It's being broadly used for education. So Jonathan and Heidi will talk about efforts going on to impact education through interactive open source textbook. And there's a ton of effort using the MOC Alliance production services to train people to address the fundamental challenges to enable industry SREs to actually stand up production clouds. The most recent sort of engagement is actually Coliseum, which is actually a massive wireless testbed that you've heard about. And for a long time, we've been engaged with the Dataverse project. This chart shows all the proposals that will be discussed on the second day of the workshop as part of the iScale, which I'm not going to try to describe it here, but these are new projects, and you can sort of see how they tightly relate to efforts that have actually been going on. So in the remainder of this session, you're going to hear about first the MGH PCC by John Goodhue. Then Mike Zink is going to actually talk about the Open Cloud Testbed. He's a PI of that effort. Scott Yokel from Harvard and Wayne Gilmore from BU, who are heads of research IT, will actually discuss the production services that real research IT are operating. And then finally, Manu Hussein from Northeastern is going to describe Coliseum, which is the newest addition to our family.